Welcome back to the Carnival Tycoon project. We are on lesson 2, and last time we were together, we were actually recording from a different location because we were stuck at home for the governor's lockdown orders, but now we are back to work. So we are on the STEM Explorer today, 38-foot mobile STEM lab here at Delta College. I want to take us just a few minutes to go over what our webpage looks like for this project and show you where to find some of the important resources. All right, so here we are on the lesson 2 portion of the webpage for Carnival Tycoon project. And you can see right here at the very top is a video lecture. Well, that's what you're watching right now. Let's show you around some of these other things like probability activities. If we click on this, you will see there are some probability activities that we have programmed in CodeApp. And we'll be using the coin flipper today. A little bit later on in the project, we'll be using a card shuffler, dice roller, and a spinner, but just the coin flipper for today. Of course, there's a link to the lecture notes, which we'll be using in just a few minutes, and these lecture notes are in multiple formats. You can use whatever one is most suitable for your purposes. Then the lesson 2 coin flip discussion questions. You'll also be answering those. It seems like there's a lot of stuff on today's lesson, and there are a lot of things, but they're all very short. We should be able to get through this in an hour. Interactive probability tree worksheet. Again, well, this is a little bit different than the other one because the other one was something for download, and this is a web page that we created. And then this is kind of fun. This is an activity that is optional at the end of today's assignment. It has to do with the NCAA bracket. Maybe you filled out one of those before. And then, of course, there are lesson 2 reflection questions in multiple formats. And finally, the practice questions, which we always have after our lessons, to see if you understand what you've just learned. And this webpage in and of itself is pretty useful because it contains a summary of all the information that we're basically going through, a little bit of the theory of what we're discussing today, a little bit of practice. And this looks kind of complicated, but it's not really that bad. And a little bit of a review at the very end with some sources listed. So this is very helpful as a companion to the video. But to start things off, we would like you to take out your lesson 2 notes for this section, and we are just going to write down a couple things, and then it'll lead us right into a fun coin flipping activity. So here we are with lesson 2 notes, theoretical versus experimental probabilities. So, theoretical probability, let's go ahead and define that. This is a mathematical calculation of what you would expect to get in a chance experiment. What you expect to get. Of course, you don't always get that. So I'm not going to write down everything in your notes because much of it is already there, but the first blank is expectations of a chance experiment. So let me just give you a simple example, one that should be pretty understandable to you at this point, especially if you've had biology class. Let's say a couple gets together, a male and a female, and they decide to have children. And we know from biology that the male can either give a sperm cell, we call these gametes, with an X chromosome, or one with a Y chromosome. The female doesn't have much choice in the matter. All of her eggs have X chromosomes so she can only give an X chromosome. So if this sperm fertilizes that egg, we have an XY, which is a male. And if this sperm fertilizes that egg, we have XX, which is a female. Now you'll notice there's a 50-50 chance, a 1 out of 2 chance, or we call that a 50-50, or if you put it into decimals, that's a 0.5 chance of having a male child, and a 1 out of 2, or a 50-50, or a 0.5 chance of having a female child. And this statistically pretty much pans out in the world where we have very, very close to 50% males and 50% females, although it's not exact, okay? That's important, especially when we get into what we call experimental probability. But let's just go on with one quick other example of theoretical probability before we do that, because if you were to pick a number between 1 and 10, for instance, see if I can get this to scroll up a little bit, a number between 1 and 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a random number. We've all done this in the classroom before. Someone says, or even at home, pick a number between 1 and 10, and you put that number behind your back. Go ahead and do it. Pick a number between 1 and 10. I've got mine. What's yours? All right. Say it out loud. It was 2. All right. I bet you were not right on that, but that's okay. You have a 1 out of 10 chance of choosing that, or 1 out of 10, or a 0.1, or you could even say 10% chance of picking that number. And we talked a little bit about that in lesson 1. All right. So that's theoretical probability, what we expect to get in a chance experiment. But, you could actually do the experiment and you could get what's called experimental probability. I'm going to write that out. Experimental probability would give us the actual results of a chance experiment when put into practice. So that couple that we were talking about a minute ago, they could have 3 girls and only 1 boy. They could have 3 girls and 1 boy if they had 4 children. I have some relatives that had all boys. My wife's aunt had 5 boys. She kept on trying, but she never got a girl. 5 boys. And, that's a low likelihood of that happening because it is 50-50 chance every single time. So now it could take me, like when we did that experiment with the pick a number between 1 and 10, it could pick me, or it could take me 3 tries, let's say, to get the correct number from 1 to 10. That is a possibility. All right. And then you'd say, well, there's a 30% chance, 30% chance of me getting it right experimentally, when theoretically it was a 10% chance. All right. So that's just a brief introduction into today's lesson on experimental and theoretical probability. But we're going to jump into a fun coin flipping activity next. All right, so for our coin flipping activity, we're going to go back to the lesson 2 webpage and go to where it shows probability activities, and go ahead and click on that. And again, we have our 4 CodeApp activities, and the one we're going to is Coin Flipper. I'm going to show you a little bit about how this works and give you a simple task. All right, the first thing I'm going to do is I'm going to make this window quite a bit larger so you can see it a little bit better as to what's going on in there. And move it over because my face is in the way. All right. So let me show you briefly how this works. It's really, really simple. Excuse me. How many coins should I flip? Well, let's just go ahead and put one coin in there and simply click go. All right. So we can see from the picture that we got heads on that coin flip, but let's take a look at what our chart looks like over on the right-hand side, because this gives us a lot of really useful information. So it shows what we have so far in our experiment on the left side: one coin and one heads. 100% heads. Total tails, 0. And the trials in our experiment are in the next column over. We only did one trial. And then all the specific details of the flips are way over here on the right-hand side. So let's do another trial. Let's go ahead and change this number to 7. All right, let's go ahead and flip 7. Go. Okay, now we have the total experiment right here on the left-hand side. And we just so happen, between those two different trials, we just so happen to have 50% heads and 50% tails. But you can see in our first trial, the data is here, we only had one head. There's no way we could have any tails there because we only had one flip. And in the second trial, we flipped 7 coins and we got 3 heads and 4 tails. All together, it gave us 50% heads. And all the results are over here. So what I would like you to do in the next couple minutes is I would like you to go ahead and do this for 1, 5, 10, 100, 1,000, and 10,000 flips. One thing about this, I want you to keep it in the same experiment. So you don't need to click new experiment. If you click new experiment, it resets. Well, if you reset it and click new experiment, it takes you back and resets the whole board. I'd like you to keep this in the same experiment. Again, 1, 5, 10, 100, 1,000, and 10,000. Go ahead and pause the video and do that activity on the Code App webpage. Hopefully you learned something in the coin flip activity. Hopefully it worked out for you. If you had any difficulty doing that, just backtrack the video just a little bit for the explanation of how to go about the activity. All right. Well, you've got some statistical information that has been collected for you on the screen in the app, and we have a few questions that we would like you to answer about that before we go on to the second part of our notes. So go ahead and answer the following questions. You will find these questions in a document on the Lesson Plan 2 webpage. Go ahead. Good luck. All right, welcome back. Hopefully, answering those questions and looking at that data got you thinking about the importance of sample size. Sample size is really important in probability and learning about probability. All right, so I'd like you to take out your notes again. We are going to finish up section 1 of lesson 2's notes. And this will be on the expectations versus results. Go ahead and take that out. We are on part C of lesson 2's notes, and I already kind of gave it away by saying this is expectations versus results. All right, so for number 1, it is expected that the results of flipping heads should have a theoretical probability of 1 out of 2 or 0.5. Just think about it. I mean, the chance of actually flipping a coin and having it land on its side are pretty much zero. You could probably do it a million times and not get it to happen even once, or maybe once, but that's effectively zero. So it's either heads or it's tails. So it's 1 out of 2. So heads. It's 1 out of 2 or 0.5. We could say also that's 50%. Now, you can go back and look at the results of your 100 flips. And this will be interesting because we will all have different results because this is a random program. So if you go back and look at that, take a look at your 100 flips and go ahead and write that information in. I'll write down the information that I got in my 100 flips. So the result of my 100 flips was, for heads that is, was 42 heads, or 42 out of 100, or 0.42 or 42%. And that would be just the opposite for the tails. So if I had 42 heads, it would be 58 tails, or 58% or 0.58. All right, so the results next of your, now even though it was expected that we'd get, I should mention, it was expected that we would get 50 and 50. I think we pretty much knew we weren't going to get 50 and 50. You could have gotten 50 and 50 just as likely as you could have gotten 42 and 58. But I got 42 and 58. All right, so for the 1,000 flips, go ahead and write that in for 1,000 flips. Oops. I will write mine in too. Mine was 572 out of 1,000, or 0.572, or we'll just round that to 57% heads in the 1,000 flips. Go ahead and do it for the 10,000 flips, and I will do the same. All right, now everybody's data is going to be different because this is a randomized program, but you'll notice that when I had 100 flips, I had 42 heads, so that was 42%, or 42 out of 100. At 1,000 flips, I had 572 heads, which was 57%, so quite a bit changed between the 100 and 1,000. But then when I went to 10,000 flips, I was back down to 49%, or 4,920 out of 10,000, 49.2% actually. So let's see how far I was off in my 100. I was off from what I expected, or my experimental was off from my theoretical. It was off by 8% here. It was only off by 7% in the opposite direction, actually, with this one. But when I got to 10,000 flips, it was only off by approximately 1%. So my theory here is if I was able to go to 10,000 flips, to 100,000 flips, then I would probably be even closer to 50%. But it's likely that I would never really get to exactly 50%. Or I could get to exactly 50%, but the likelihood is low. So that's expectations versus actual results. Expectations will give you, of course, your theoretical probability, and the actual results will give you your experimental probability. Have any of you ever watched The Bachelor or The Bachelorette? Think about that show for a minute. You start out, let's take The Bachelorette, for instance. You start out with 20 guys. I think it's about 20 guys. Let's say it's 20. And you've got one girl, and all of them are single. And, of course, the other girl is looking for love and hoping to find it with one of those 20 men that have come on the show taking their chance at love, too. So let's think about that for a second. They have to whittle that down. The girl has to whittle that down. She can't, she has to use some kind of criteria to figure out how she's going to narrow it down to the one person that she's going to decide to move forward with in her relationship. So I want to show you something about that. So let's think about this for a minute. We start out on The Bachelorette, and we've got, you're on the show as a male on the show at the very, very beginning of the show, and there are 20 of you. And after the first episode, after she's had a chance to spend a few minutes with you talking about things and just learning a little bit about you, she is supposed to whittle that down by half. So she's going to send half of the people home, and she's going to keep half of the guys around. So it's either a yes or a no. I guess we'll put a little smiley face here for the yes, because that means you get to stick around for at least one more episode. And a no, oh, I'm very, very sad. I have to go home in the car. All right. So she's going to send half of them home. So that gives a 50% chance of being able to stick around in this show for another episode, and a 50% chance of being sent home. Or one half of the guys are staying, and one half of the guys are going home. Well, what is one half of 20? It's a pretty easy math problem there. That would give us 10. Okay? 10 went home, and 10 got to stay. Well, as the show goes, she then gets to spend some more time with these 10 people that she decided to have stick around, and they all get to go on individual dates and do some fun things, and skydiving, or all the things that they do, and she has to make a decision again. But, they don't want the show to be over too quickly, so they say, all right, so you need to whittle this down a little bit further. You're going to send 2 people home from this group that got to stay. Oh, that's such a difficult decision for her. So again, it's either a yes or a no. 2 out of 10, or that would be 1 out of 5, have to go home. But 4 out of 5 get to stay. 4 out of 5 is 80%. 80% get to stay, 20% have to go home. 80%, 4 out of 5. 4 out of 5, well, there's 10 people there, so the people that get to stay would be 8 people. So we're left now with 8, and 2 had to go home. Again, very, very sad, had to go home. So there are 8 people remaining. 8 people of the original 20 are remaining. That's important because we'll talk about that in a second. Well, then she has to whittle it down again. She spends more time, and she goes on more dates and has more romantic excursions. And then the show says that she has to cut it in half again. So she does that again. There's a yes and there's a no. and 50%, if she's cutting it in half, have to go. 50% of the 8, that's 4 people are going home, all sad and depressed, and 4 people, 50%, or 1/2, or 4 people are yeses. Well, you know how this goes. You've got those 4 happy people, and this is usually at the point in the show where they go visit the parents and do all that fun stuff, and eventually she has to make that decision about those 4, and that's either going to be a yes or a no. Well, 75% of those have to go home all sad, and 25%, or 1 out of 4, they win the prize, and hopefully they live happily ever after. Okay, sorry, you couldn't see that on there. Hopefully they live happily ever after. Now, the point of this is, what we've actually drawn here is basically a probability tree. And we're going to go back to we'll look at the bottom of it first, because let me erase some of these little stray marks. 25% at the very end, 25% of the guys at the very end got to like win the girl, I guess. But that's not 25% of everybody. That's only 25% of the people that were remaining at this point right here. Okay? And that was 50% of the people who were remaining at this point here. And that was 80% of the people that were remaining at this point here. And that was 50% of people who started the show. So how this works is it's really simply multiplying by fractions. So we have 1/4 at the very bottom, 1/4 of 1/2 of 4/5 of 1/2 of 20. So if we go 20 times 1/2 times 4/5 times 1/2 again, and then times 1/4, the very, very end, we actually get our one happy contestant on The Bachelorette. That is a probability tree. So we're going to give you an opportunity to fill out a basic probability tree, and we've created one online. So go ahead and go to the lesson plan page, and you can find the probability tree worksheet, and it will take you directly there, and I'll show you how that works. So here we are back on the lesson 2, empirical probabilities versus probability trees, and probability trees lesson plan page. And you can see right down here, there's an interactive probability tree worksheet. So we want to go ahead and click on that, and it will take us to a web page where you can actually fill it out. So you can put your name in here. So my name is Nathan Elder, so I'm going to go ahead and fill that in right now. Suppose you are turned into an ant. And once you've done panicking, you start walking from the top of this tree to the bottom. You aren't sure which way to go, so you bring a tiny ant-sized coin with you, and you flip it before leaving each box. If it comes up heads, you crawl along the arrow labeled H, and if it comes up tails, you crawl along the arrow labeled T. In each box, fill in the probability that you'll end up crawling through it. There is one spot to enter it as a fraction and another after the equal symbol to enter it as a decimal. Fill in both. We've done the first one for you because it is obviously the hardest. Yeah, clearly. All right, so you're an ant and you have choices where you're going to go, but you don't know how to make those choices, so you bring your tiny little ant-sized coin with you. All right, so Here we have 1 out of 1 equals 1.0. If the ant reaches, has a choice right here at this point, he goes ahead and flips his coin. If he gets heads, what are the chances of getting heads? Well, I'll actually help you out with the first one. 1 out of 3? No. 1 out of 2, of course. And what is 1 out of 2 as a decimal? It is 0.9. Wait. No, it's 0.5. All right. So then he has another decision to make and another decision until you have all these possible outcomes of where the ant could end up at the end of the little excursion. So we'll go ahead and let you go to the web page, the probability tree worksheet, and work that out for probability trees. Best of luck to you. Oh, one last thing. If your teacher wants to collect this probability tree activity, there are directions on the website where we previously were. I'll show you. In the help section, this tells you how to save and print your probability tree so you can turn it in, and it gives a couple different options for that if your teacher requires you to do so. Best of luck on the probability worksheet. Hopefully you didn't have too much problem filling out the probability tree worksheet online, or saving it, or printing it, or doing it whatever your teacher has asked you to do. But now we have some discussion questions that we'd like you to answer. Welcome back. We're moving right along in the probability lesson 2 for the Carnival Tycoon project. You've done quite a few different little things so far, and we are going to now, so we can wrap that up. We'll be working on Roman numeral 2 using probability trees to predict outcomes. So we're ready to continue with our notes on probability trees and how they affect outcomes. All right, so what is a probability tree? Well, I think you have a pretty good idea of what it is so far. It is a visual, this is important, it's a visual representation of the pathway to possible outcomes. And a few minutes ago, I had you answer a few questions. What were the chances of rolling some certain things, like rolling heads on your first flip or whatnot? So let's take a look at that with probability trees. So for number 1, how about if we were to roll heads and another heads? Well, each one of those had a 0.5 chance. 0.5, or 1/2. And we can go back to a probability tree. So we take the coin, and we know we can get heads or tails. If we go the route of heads, that was a 1/2 chance. But then we flip again, and of course we have heads or tails. So then again it's another 1/2 chance to get a heads and then another heads. So that's why we have heads is 1/2, and we actually multiply these things together. 1/2 times 1/2 equals 1/4, or 0.25, or that's 25% chance. How about heads? Oh, that's a lot of heads in a row. Heads. Well, again, it's the same general concept of 1/2, and then 1/2 again, and 1/2 again, and 1/2 again, and those all just get multiplied times each other, and 1/2 times 1/2 is 1/4, times 1/2 is 1/8, times another half is 1/16, or 1/16, or 0.0625. All right. Now you can see the chances are going down and down. How about if we were going to get the pattern heads tails heads, tails. Now, this is what confuses people sometimes, because no, we're not getting all heads in a row, but there's still a 50% chance of getting any one particular thing when you flip a coin. So when you flip a coin, and you have, looks like I might have missed one. Looks like I got a little bit off in my numbering, but that's okay. I think you get the concept. If we flip a coin and we get heads, tails, heads, tails, when we first flip it, we know that to get this heads, it's a 1/2 chance, because every coin we flip is a 1/2 chance of head or tails. But when we flip it again, this tails is also a 1/2 chance. So to get tails, it would be 1 out of 2. And to get heads the next time, it would be 1 out of 2. And to get tails the next time, it would be 1 out of 2. So it is not different. It is 1 out of 16, or 0.0625. Even though it's not HHHH or TTTT, it's HTHT. Now we're talking about this in successive events, or heads, tails, tails. All right, so to calculate the probabilities then of successive events using a probability tree, the fractions are multiplied. That's important. So to get 20 heads in a row, for instance, that would be very unlikely, wouldn't it? So 20 heads in a row, that would be quite a lot of math to do. We'd have heads, dot, all the way to 20. And each time you flip the coin, it would be a 1/2 chance of getting heads, times 1/2 times 1/2. And think about this. If you ever flipped a tails at any time during that event, then you'd be failing. You could not get your 20 heads. So to do this, you'd have to have an extreme amount of luck. As a matter of fact, 1/2 times 1/2 times 1/2 multiplied up to 20 times is actually a really, really low number of 1 out of 1,048,576, or let's go ahead and put that in as a fraction, and there's just a lot of zeros involved here, 0.00000095. Wow, that's a really small chance. Maybe you ought to think about this next time you are tempted to buy a lottery ticket. We are getting really close to wrapping up our lesson 2 on experimental versus theoretical probabilities. But we have a couple other things left to do. One of which we think is pretty fun. It is a bonus activity on an NCAA bracket. And if your teacher asks you to do this activity, I want to show you right now how to do it. So let's go take a look at the website once again, and you can see where this is located. So here we are back at the Lesson 2 web page. All these different links we showed you before, and if you scroll down here near the bottom, we get to where it says college basketball, empty college basketball bracket. Now in 2020, we actually did not get to fill out one of these brackets because they canceled the tournament, and that is why this bracket is empty on both sides. If you're not familiar with how the NCAA tournament works, is there are a couple play-in games, but once the play-in games have been played out, all of the teams, the 64 teams that made the tournament, are placed in 4 different regions. One region up here with 16 teams, and another region down here with 16, and the same on the other side, and that gives us 64 teams that have a chance of winning the national championship. And the women's bracket and the men's bracket are exactly the same. All right, so your school, if they made it into the tournament, would be placed somewhere along one of these lines here. And you can see it's basically like a probability tree, starting out with a large number and converging on this one team here that's going to play against this one team here. So here's what we'd like you to do for this activity is we'd like you to pick your favorite basketball team and place them over on one of the lines on this side, and it honestly doesn't matter where they get placed. Next, we want you to take your least favorite basketball team. I definitely have a favorite and a least favorite basketball team. Hopefully you do too. And you can place them somewhere over here on the right. And we would like you to determine what is two things, actually. What is the likelihood of your two teams, your favorite and your least favorite team, making it to this national championship game right here? So your favorite and your least favorite. And then finally, the second thing we'd like you to figure out is then what would be the likelihood of your favorite team not only making it to the game, but actually winning the game. It involves a little bit of math, not quite a bit of math, but you can expect some decimal points involved in this one, okay? Now, the only difference between this and reality is that we're going to say that there's a 50% chance when two teams come together and play each other, there's a 50% chance of winning for both teams. That's honestly not the case experimentally, because it's very, very rare for a team that barely makes it in the tournament and is put down at a 16 seed to beat a 1 seed, for instance, or a 15 seed to beat a 2 seed. But we're going to assume that they have an equal chance to win. All right? Best of luck to you. Let's see what you can find out about this NCAA bracket. All right, your teacher may or may not have had you do that bonus activity on the NCAA bracket. We think it's of great value to do. All right, but here we are at the end of the assignment today, and we have two more things left. We have some reflection questions. So we would like you to answer the reflection question in your, you're going to see that is on the webpage also, the reflection question. So you'll download it and answer that question and turn it in to your teacher. It's important to see if you have understood some of the things that you've learned today in lesson 2. And then also after that, you will have the practice questions that go along with lesson 2. So let me give you a short reminder, a brief reminder of where those things are located on the website. So here we are back on the website. And right here at the end, you've got lesson 2 reflections. And again, they're in multiple formats. And you have the practice questions that go along with lesson 2 that are also in multiple formats. So there you go. Lesson 2 is in the books on theoretical versus experimental probability. Awesome job. We'll see you next time.